In the autumn of 1939, British Naval Command treated Scapa Flow as a solved problem. The anchorage was classified as effectively immune to submarine attack based on physical constraints rather than continuous defensive action. The eastern approaches were obstructed by block ships sunk at Kirk Sound and Scary Sound. Navigable gaps were estimated at under 50 meters in width. Depths fluctuated between 9 and 15 meters, while tidal currents during peak flow reached up to 8 knots. For a submarine with a draft near 4.7 meters, limited turning authority at low speed, and a pressure hull intolerant of grounding, these parameters were considered prohibitive. The core assumption was mechanical finality. Geometry would deny access before intent could matter. This assumption shaped the defensive architecture. Patrol density inside the anchorage was minimal. Hydrofoam coverage was incomplete and degraded by seabed clutter and variable salinity layers. Anti-submarine doctrine emphasized exclusion rather than rapid reaction. The system was not designed to respond quickly to intrusion because intrusion was not expected to occur. Its limiting factor was confidence in static barriers. Once access was judged impossible, response latency became irrelevant. German Naval Command evaluated the same environment differently. Scapa Flow was not dismissed as unreachable. It was treated as a boundary case where success depended on coincident failure across multiple constraints. U-47 was a Type 7B submarine with a surface displacement of 753 tons, a submerged displacement exceeding 850 tons, and a battery system that imposed strict limits on submerged maneuver. Above 4 knots submerged, battery discharge accelerated nonlinearly. Below 2 knots, acoustic output dropped faster than energy consumption increased. Between these values existed a narrow operational band where time and silence could be exchanged at tolerable cost. This band was unstable. Deviations of fractions of a knot altered both endurance and detectability. The technical anchor was nonlinear battery depletion. Speed errors translated directly into lost time or increased exposure. U-47 departed Kiel on October 8, 1939, under Captain Lieutenant Gunther Preen, carrying 14 torpedoes, including G7E electric models with a nominal speed of 30 knots and warheads of approximately 280 kilograms. The weapon load defined engagement capacity but did not determine feasibility. In confined waters, destructive power was secondary to navigational precision. A single course correction executed too late would exceed available maneuver space. Once committed, there would be no room to recover. As the submarine transited north toward the Orkney Islands, environmental conditions began to close margins. Cloud cover limited celestial navigation. Dead reckoning became the primary positional reference. With each hour without a confirmed fix, the probable error ellipse expanded. Ahead, the usable corridor narrowed. This produced a convergence problem. Positional uncertainty increased while tolerance decreased. In waters where safe clearance was measured in meters, accumulated lateral error became a physical threat. The technical anchor was error accumulation over time. Correction required heading changes that could not be executed safely under strong current at minimal speed. On the night of October 13, 1939, U-47 approached the eastern entrances during a flooding tide. This choice reduced relative current when moving with the flow, allowing propulsion to be minimized. Engines were stopped. The submarine became a passive mass, carried by a predictable vector. At speeds approaching 1 knot, rudder effectiveness degraded sharply. Control inputs lagged by seconds. Turning radius expanded beyond available space. In this regime, the primary risk was not detection but loss of control. Contact with steel wreckage or uneven seabed could not be avoided once yaw developed. The technical anchor was delayed hydrodynamic response. Below a critical speed, steering ceased to be corrective and became merely reactive. The gap between the block ships was not an engineered channel. It was the result of gradual movement under tidal stress. British defenses assumed static obstruction. They did not continuously verify gap geometry. U-47 passed through a space measured in tens of centimeters, with underkeel clearance reduced by tidal variation and silt accumulation. This maneuver depended on precise timing, stable current, and exact alignment. Any deviation would have resulted in grounding with no recovery option. Inside Scapa Flow, the vulnerability shifted. Capital ships lay at anchor under readiness assumptions inherited from peacetime and previous war experience. HMS Royal Oak, a Revenge-class battleship displacing over 29,000 tons with belt armor up to 330 millimeters, was not configured for an underwater threat originating inside the perimeter. Anti-torpedo nets were incomplete. Watertight discipline was relaxed. Watch routines prioritized surface and air approaches. The weakness was temporal. The system required minutes to transition from nominal readiness to full defensive posture. Those minutes were not available once a submarine was already inside the anchorage. At 0:58 on October 14, 1939, U-47 fired its first torpedoes. Early war German torpedo systems suffered from depth-keeping errors and magnetic pistol malfunctions. Detonations were inconsistent. One explosion produced an ambiguous signature that did not immediately map to an external torpedo strike. Classification was delayed. No immediate general alarm followed. The technical anchor was misclassification latency. When escalation depends on confirmation, ambiguity extends the attacker's effective window even in the absence of stealth. The second firing sequence followed not because conditions improved, but because the defensive system had not yet transitioned states. At 1:16, U-47 launched additional torpedoes from close range, reducing gyro angle error and partially compensating for depth-keeping uncertainty. Multiple impacts occurred amidships. Flooding advanced along longitudinal compartments faster than internal countermeasures could be executed. Royal Oak's subdivision scheme assumed damage limited to a narrow arc, not simultaneous ingress across multiple frames, while the ship lay at anchor with reduced watertight discipline. Pump capacity was finite. Valve closure required time. Once ingress rate exceeded isolation speed, stability margins collapsed. Capsize followed within minutes. The decisive variable was flooding velocity relative to response time. When water volume increases faster than corrective action can propagate, the outcome becomes mechanically irreversible. U-47 did not remain to assess results. Battery state and exposure geometry dictated immediate withdrawal. Alert propagation inside a harbor is nonlinear. Once an underwater attack is correctly classified, patrol vectors intersect, search assets multiply, and probability concentrates rapidly. Every additional minute inside Scapa Flow increased the likelihood that independent defensive elements would synchronize into a coherent response. The technical anchor was convergence time. Escape probability decayed sharply once multiple units began operating against a single inferred contact. The exit retraced the ingress route under ebbing tide conditions, now opposing movement. This forced intermittent propulsion to maintain heading. Full silence surrendered control. Continuous power accelerated detection. The submarine alternated short, powered corrections with passive drift, attempting to remain within the same narrow corridor used on entry. Navigation error that could be tolerated during approach became lethal during withdrawal, because correction against current required higher thrust and longer exposure. The limiting factor shifted to cumulative detectability. Each powered correction added marginal risk. Survival depended on the sum of those margins remaining below a threshold until clear water was reached. British response unfolded unevenly. Initial reports moved through communication chains optimized to prevent false alarms rather than to compress reaction time. Shore stations, patrol craft, and command centers operated on sequential escalation protocols. Confirmation was required before authority passed downward. This structure reduced peacetime error, but imposed delay under penetration conditions. The interval between the first confirmed sinking and the establishment of a coordinated search was measured in tens of minutes. U-47's exit window was shorter. The technical anchor was decision cycle latency. Information traveled slower than the intruder. German Naval Command, tracking radio silence and expected patrol timelines, began to classify U-47 as lost. This assessment reflected doctrine rather than emotion. A submarine operating beyond modeled survivability envelopes was expected to be removed by at least one independent defensive layer: mines, patrols, grounding, or detection. Survival required the simultaneous non-activation of all of them. Doctrine treated that concurrence as statistically negligible. When U-47 surfaced days later, the outcome forced reassessment not of bravery, but of assumptions embedded in operational models. British countermeasures moved first through engineering rather than patrol augmentation. Temporary measures were rejected as insufficient. The anchorage could not depend on vigilance or interpretation. Permanent structures were required to remove variables entirely. The Churchill barriers were conceived to eliminate depth as a factor. Resting on the seabed and sealing the eastern approaches, they removed underkeel clearance and converted Scapa Flow from a probabilistic defense into a geometrically closed system. Once completed, no submerged vessel with a pressure hull could pass, regardless of speed, noise, or timing. The technical anchor was absolute depth denial, a constraint that does not degrade with fatigue, misinterpretation, or delayed reaction. The implications extended beyond the anchorage. Harbor defense doctrine shifted toward physical impossibility rather than layer detection. Convoy escort doctrine shifted toward compressing classification and response cycles. The vulnerability exposed was not blindness, but delay. Detection without rapid interpretation proved insufficient. German submarine command absorbed a parallel lesson. Penetration success depended on concurrence across variables that could not be reliably reproduced. Tide phase, illumination, navigation error, enemy readiness, and battery state had to align within narrow tolerances. The constraint was repeatability. An operation that could not be executed under a broad range of conditions had limited strategic value. As the Atlantic campaign expanded, both sides encountered sustainability limits. British escorts increased patrol density and shortened watch cycles. Reaction speed improved briefly, then degraded as fatigue accumulated. Sonar operators missed marginal contacts as perceptual thresholds shifted under constant noise exposure. Equipment drifted out of calibration. German submarines experienced incremental mechanical degradation. Battery capacity declined over repeated charge-discharge cycles. Fuel consumption crept above nominal rates. These losses were individually small but cumulative and irreversible during a patrol. The technical anchor was degradation over time. Endurance eroded regardless of tactical success. Doctrinal adjustments redistributed rather than eliminated risk. Authority was decentralized to reduce response delay, increasing false positives and material expenditure. Depth charges were released against ambiguous contacts. Fuel and ordnance consumption rose. Maintenance throughput became the limiting factor. Aggressive defense shortened reaction time, but accelerated wear. The sea imposed a conservation principle. Gains in immediacy produced losses in sustainability. Scapa Flow receded from immediate operational focus, but its structural implications persisted. It demonstrated that presumed sanctuaries exist only until their boundary conditions are tested. Once those conditions fail, responses tend to harden systems, closing one vulnerability while opening others elsewhere. From that point forward, naval warfare evolved as a continuous negotiation with limits imposed by physics, time, and human capacity. Decisions mattered most before they appeared dramatic, because once thresholds were crossed, outcomes followed mechanically, with little room for correction. The Admiralty's internal reviews treated the Scapa Flow penetration as evidence that defenses anchored in assumption degrade invisibly. Prior evaluations had modeled the anchorage as a static obstacle field whose effectiveness declined slowly and predictably. U-47 exposed a different failure mode. Block ships shifted under tidal loading. Sediment migrated along the seabed. Narrow gaps appeared intermittently, without triggering alarms, because no continuous measurement existed to detect them. The technical anchor was unverified drift. A system that is not periodically remeasured accumulates hidden error until it fails abruptly rather than gradually. Engineering replaced interpretation. Temporary countermeasures were judged insufficient because they preserved variability. Permanent causeways were designed to eliminate degrees of freedom entirely. The Churchill barriers were specified to sit on the seabed with mass sufficient to resist scour and storm surge, converting open water into impassable geometry. Once installed, they required no watch cycle, no classification, and no decision loop. The limiting factor moved from human performance to construction capacity and material throughput. Security became a function of concrete volume and placement accuracy. Fleet posture adjusted accordingly. Concentration within a single anchorage magnified the consequences of breach. Dispersion reduced that risk but increased exposure during transit. Capital ships relocating between bases spent extended periods in predictable sea lanes, constrained by depth contours and navigation requirements. The technical anchor here was exposure duration. A ship protected by geography at anchor traded that protection for hours or days of vulnerability while underway. Security became time-dependent rather than positional. German submarine command internalized the complementary lesson. Exceptional penetration was not strategy. It was an edge case dependent on concurrence across variables that could not be aligned on demand. Doctrine shifted toward operations that could be executed repeatedly within broader tolerances. Attrition replaced penetration. Patrol plans emphasized endurance management, battery preservation, and withdrawal geometry over singular success. The constraint was operational repeatability. Strategic value favored actions whose success probability remained stable across changing conditions. In the Atlantic, these principles governed convoy warfare. Escorts and submarines operated within narrowing envelopes defined by maintenance cycles and crew endurance. British destroyers and corvettes accumulated engine hours at rates that outpaced refit capacity. Vibration fatigue, bearing wear, and salt ingress increased failure probability independently of combat. German submarines experienced analogous degradation. Battery cells lost capacity unevenly, complicating charge management and reducing usable submerged time. Diesel engines accumulated hours beyond optimal service intervals, raising fault incidents under load. The technical anchor was latent degradation. Systems failed not at peak demand, but after cumulative stress had already narrowed options. Tactics adapted to manage thresholds. Submarine commanders planned engagements backward from withdrawal feasibility, prioritizing clear escape vectors aligned with current and depth over optimal firing geometry. Escorts curtailed pursuit once fuel state or machinery limits approached predefined cutoffs, accepting that some contacts would escape. The technical anchor was threshold discipline. Once limits were reached, disengagement was automatic, regardless of opportunity. These practices produced an operational equilibrium. Neither side achieved absolute control. Instead, each sought to impose higher cumulative strain on the other systems than its own could sustain. Attrition occurred continuously, even without contact. Patrols that detected nothing still consumed machinery life and crew stamina. Convoys that arrived intact still depleted escorts. Time itself became an adversary. Within this framework, Scapa Flow remained instructive as an early signal. It showed how confidence built on unverified conditions can mask accumulating risk, and how correcting that risk requires commitments that reshape future choices. Concrete barriers reduced flexibility. Fleet redistribution increased transit exposure. Each correction displaced risk rather than erasing it. As naval operations continued, planning increasingly emphasized resilience over perfection. Systems were evaluated by behavior under sustained load and by recovery timelines after degradation. Success depended less on dramatic action than on preserving function as margins narrowed. The sea enforced these terms impartially. It rewarded systems that acknowledged limits early and punished those that attempted to exceed them. As these adaptations settled into routine, Naval Command began to quantify limits that had previously been implicit. British escort doctrine incorporated explicit engine hour ceilings and fuel burn thresholds into patrol orders. A destroyer rated for 30 knots was no longer evaluated by maximum output, but by how many hours it could sustain 18 to 20 knots before vibration and thermal stress accelerated bearing wear and shaft misalignment. The technical anchor was sustained power tolerance. Performance measured at peak output proved irrelevant once operations extended across days rather than minutes. Escort formations were adjusted accordingly. High-speed pursuit was restricted to contacts that met defined classification confidence levels. Ambiguous signals no longer justified prolonged full-power chases. Instead, escorts favored containment patterns designed to constrain submarine movement over time, forcing repeated depth and course changes. This approach treated the submarine as an energy-limited system rather than a target to be destroyed immediately. The constraint was asymmetric endurance. Surface escorts could refuel and refit. A submerged submarine could not restore battery capacity while evading. German submarine command refined battery management in response. Patrol instructions emphasized preserving submerged endurance for the withdrawal phase, rather than expending it during approach. Battery charge percentages were tracked continuously, and engagement was discouraged if projected reserves fell below minimum values required for evasion under pursuit. A submarine entering combat with depleted batteries faced a binary outcome: attack and risk immobilization, or disengage without firing. The technical anchor was minimum viable energy reserve. Below that threshold, tactical choice collapsed regardless of target opportunity. Environmental factors further narrowed margins. Winter Atlantic conditions increased background noise, degrading sonar discrimination while simultaneously complicating depth control for submarines. Heavy seas induced vertical motion that interfered with periscope stability and increased hydrodynamic drag. For escorts, rough weather reduced effective speed and raised fuel consumption rates above planning assumptions. The limiting factor was sea state inefficiency. Weather imposed additional cost on every maneuver without favoring either side consistently. These inefficiencies accumulated invisibly. A patrol shortened by mechanical fault did not register as a defeat, yet it reduced coverage. A submarine forced to disengage early preserved its hull, but surrendered operational space. Over time, such marginal outcomes shaped the strategic picture more reliably than singular engagements. The technical anchor here was cumulative opportunity loss. Missed contacts and aborted actions altered outcomes without producing discrete events. Industrial capacity increasingly dictated tempo. British repair yards became bottlenecks as escort wear outpaced maintenance throughput. Dry dock availability, skilled labor hours, and spare part flow determined how quickly degraded ships could return to service. Ships awaiting overhaul represented defensive capacity temporarily removed from the system. The constraint was regeneration latency. Even a materially superior navy could not restore assets instantaneously. German industry faced parallel limits. Submarine production increased, but training pipelines and experienced crew availability lagged hull output. Newly commissioned boats operated with reduced effectiveness, increasing mechanical mishandling and navigational error rates. The technical anchor was human-machine coupling. Complex systems delivered optimal performance only when matched with trained operators. Deficiencies in one degraded the whole. By this stage, naval warfare had shifted decisively away from the search for decisive moments. Planning focused on preserving system integrity across repeated cycles of strain. Actions that produced immediate tactical success at the cost of accelerated degradation were increasingly avoided. The war at sea became a contest of pacing. Each side sought to operate just below thresholds where wear, fatigue, and error would compound uncontrollably. In that context, the penetration of Scapa Flow retained significance not as a model to replicate, but as an early demonstration of what occurred when assumptions exceeded validated limits. Once those limits were understood, doctrine adapted toward endurance and recovery rather than singular feats. The sea imposed these constraints consistently. It did not reward excess. It enforced balance through failure, until one system could no longer absorb pressure and continue to function. As these constraints became institutionalized, naval staffs began to plan not for ideal conditions, but for degraded ones. British operational orders increasingly assumed partial sensor failure, delayed reporting, and reduced escort availability as baseline rather than exception. Convoy protection schemes were therefore designed to remain functional even when individual elements dropped out. The technical anchor was redundancy under attrition. A system that required all components to operate at full capacity was judged brittle. One that tolerated loss without collapse was preferred. This logic reshaped convoy geometry. Spacing between merchant vessels was adjusted to balance sonar shadow reduction against collision risk under blackout conditions. Tighter spacing improved collective detection, but reduced maneuvering freedom once an attack occurred. Wider spacing increased evasion options, but created acoustic gaps exploitable by submarines. The constraint was spatial trade-off. No configuration maximized both detection and maneuverability simultaneously. Each choice privileged one at the expense of the other. German submarine commanders exploited these trade-offs by positioning boats along predictable convoy tracks where course changes were constrained by traffic separation, depth contours, or weather. Engagement timing was selected to coincide with moments when escorts were least able to maneuver aggressively without risking collision or losing contact elsewhere. The technical anchor was maneuver restriction. A convoy limited in its ability to turn or scatter presented a narrower but more stable target environment. Withdrawal planning remained central. Submarines that attacked too early extended their exposure window. Those that waited too long risked battery depletion before escape. Optimal timing depended on sea state, escort pattern, and remaining energy reserve. This balance point shifted constantly. The constraint was dynamic margin. Tactical decisions were made within envelopes that changed hour by hour, closing rapidly once contact occurred. British escorts responded by emphasizing persistence over speed. Rather than brief high-speed chases, they adopted longer containment sweeps at moderate speed, forcing submarines to remain submerged and drain batteries. This approach reduced immediate kill probability, but increased cumulative pressure. The technical anchor was forced endurance expenditure. Each hour a submarine remained submerged without opportunity to recharge narrowed its operational horizon. Mechanical strain followed. Escorts maintaining moderate speed for extended periods accumulated engine hours rapidly, increasing maintenance demand. Submarines executing prolonged evasion cycles experienced uneven battery discharge, complicating power management and increasing the risk of sudden capacity loss. These stresses were not dramatic, but they were decisive over time. The constraint was uneven wear. Systems degraded irregularly, forcing conservative assumptions and earlier withdrawal. Strategic planners increasingly measured success in terms of system survival rather than engagement outcome. A convoy that arrived intact but forced escorts into early refit represented a mixed result. A submarine that survived but returned with critically degraded batteries or engines represented lost future capability. The technical anchor here was residual capacity. What mattered most was how much usable system remained after the encounter. In this environment, Scapa Flow's relevance persisted as a reference for boundary failure rather than tactical inspiration. It illustrated how a single misalignment between assumption and reality could cascade into structural change. British defenses eliminated that specific vulnerability permanently, but at the cost of flexibility and resources that shaped subsequent operations. German doctrine absorbed the lesson that exceptional success narrowed rather than expanded future options by inviting countermeasures that closed the window entirely. As the war progressed, naval conflict settled into a pattern governed by controlled exhaustion. Neither side sought decisive confrontation at all costs. Both operated within limits imposed by physics, logistics, and human endurance. Gains were incremental. Losses accumulated quietly. Outcomes were determined not by singular brilliance, but by which system maintained coherence longer under sustained pressure, until one side's margins collapsed beyond recovery. As these operational patterns stabilized, the margin between effectiveness and failure narrowed further. British command began to treat escort groups as consumable units with predictable degradation curves. Patrol orders incorporated maximum continuous operation limits, not as safety guidance, but as hard constraints. Exceeding them was expected to trigger accelerated failure rather than incremental wear. Engines operating beyond thermal equilibrium accumulated microfractures. Lubrication breakdown increased bearing friction. Crew error rates rose measurably after defined watch-hour thresholds. The technical anchor was nonlinear fatigue. Beyond specific usage points, systems degraded faster than planners could compensate. This understanding altered how losses were interpreted. A destroyer withdrawn for refit after weeks of continuous patrol represented a delayed loss, not a preserved asset. Its absence reduced coverage elsewhere, creating secondary vulnerabilities. Protection was no longer evaluated locally, but as a network effect. Removing one node redistributed strain across adjacent nodes until they, too, approached failure thresholds. The constraint was load redistribution. Stress removed from one area reappeared amplified in another. German submarine command encountered the same phenomenon in reverse. Each patrol shortened the effective lifespan of the boat, even if no damage was recorded. Battery cells degraded unevenly, producing unpredictable voltage drops under load. Electric motors developed vibration signatures that increased detectability at specific RPM bands. These effects were subtle but cumulative. A submarine that returned intact was not identical to one that had never sailed. The technical anchor was irreversible degradation. Time at sea permanently altered system behavior. These realities shaped engagement doctrine. Submarines avoided aggressive maneuvering not out of caution, but because abrupt depth changes and high-speed turns pushed degraded systems toward failure. Escorts likewise reduced sharp course reversals that strained steering gear and propulsion shafts. Engagements became smoother, slower, and longer, not because either side preferred them that way, but because mechanical limits enforced that tempo. The constraint was kinematic gentleness. Sudden motion carried a disproportionate cost. Strategic planners recognized that industrial capacity now defined the outer boundary of naval power. Shipyards, repair facilities, and training establishments determined how quickly degraded systems could be restored or replaced. Britain's ability to expand escort production and maintenance throughput gradually shifted the balance, not through tactical superiority, but through regeneration rate. German production increased, but training and crew integration lagged behind hull output. A submarine delivered without a fully seasoned crew entered service, with reduced reliability. The technical anchor was integration delay. Hardware availability outpaced effective operational readiness. Over time, the Atlantic conflict resolved into an asymmetry of recovery. One side could afford cumulative wear because it could replace and repair faster than the other. The opposing side faced diminishing returns as each patrol consumed a larger fraction of its remaining effective capacity. Tactical encounters reflected this imbalance indirectly. Escorts grew more numerous. Coverage gaps narrowed. Submarines found fewer opportunities to disengage cleanly without incurring unsustainable stress. In this phase, Scapa Flow's legacy was fully absorbed. The event was no longer cited explicitly, but its lesson governed behavior. Assumptions were treated as liabilities until proven continuously valid. Static defenses were engineered to remove variability. Mobile forces were paced to avoid catastrophic degradation. Risk was accepted only when its long-term cost could be absorbed. By the later stages of the war, naval warfare had become a controlled process of exhaustion. Victory belonged not to the side that struck hardest, but to the side whose systems degraded more slowly and recovered more reliably. The sea enforced this outcome impartially. It amplified small advantages in endurance and maintenance until they became decisive. What began in 1939 as a challenge to presumed security ended as a demonstration that modern war at sea was governed less by moments of surprise than by the arithmetic of limits, sustained over time until one system could no longer continue. When placed against the full duration of the naval war, the appearance of U-47 inside Scapa Flow no longer reads as an isolated breach, nor as a singular triumph. It becomes an early exposure of how maritime systems behave when their design assumptions are pushed beyond validated limits. The anchorage failed not because defenses were absent, but because they were optimized around average conditions rather than edge states where physics, time, and human latency converge simultaneously. Before October 1939, British confidence in Scapa Flow rested on static parameters. Depth, obstruction, and current were treated as constants. Readiness was assumed to be available on demand. The penetration demonstrated that none of these variables were fixed. Blockships shifted under tidal load. Gaps opened intermittently. Currents altered clearance by tens of centimeters. Readiness existed only after a measurable delay. The system did not collapse catastrophically. It failed briefly, and that brief failure was sufficient. The technical anchor was boundary validation. A defense that is not continuously revalidated accumulates error until its margin disappears without warning. The British response did not attempt to restore security through vigilance alone. It replaced uncertainty with mass and geometry. The Churchill barriers removed depth and passage width as variables entirely, converting a probabilistic defense into a deterministic one. This solution was effective, but not neutral. It fixed one problem permanently while committing resources and reducing flexibility elsewhere. Once installed, the barriers could not adapt. They traded responsiveness for certainty. That trade defined much of the subsequent war at sea. Wherever human-operated systems proved unreliable under sustained load, they were replaced or constrained by physical structures that did not fatigue. German naval command absorbed a parallel lesson. The success of U-47 did not widen operational freedom, it narrowed it. An outcome that depended on rare concurrence invited countermeasures that closed the window completely. As the war progressed, submarine doctrine moved away from exceptional penetration toward operations that could be executed repeatedly under degradation. Endurance, withdrawal feasibility, and preservation of system margins became dominant considerations. Tactical opportunity was increasingly rejected if it imposed irreversible cost on future capability. Across the Atlantic, these logics converged. Escorts, submarines, and merchant traffic all operated within tightening envelopes defined by maintenance throughput, fuel availability, battery capacity, and crew endurance. Detection systems improved incrementally, but remained bounded by noise, delay, and interpretation. Speed provided short-term advantage at the cost of accelerated wear. Time imposed cumulative penalties that could not be offset tactically. The decisive variable was no longer surprise or firepower, but regeneration rate, how quickly a system could recover usable capacity after absorbing stress. By the middle years of the war, outcomes at sea were shaped less by individual encounters than by aggregate degradation. Convoys arrived or failed not solely because of tactics, but because escorts reached or exceeded sustainable operating thresholds. Submarines survived or were lost not only through detection, but through mechanical limits reached during evasion. Victory accrued to the side that managed decline more effectively, replacing worn machinery and exhausted crews faster than its opponent, and avoiding irreversible loss while forcing it elsewhere. Seen at this scale, Scapa Flow stands not as an anomaly, but as an early signal. It revealed how quickly presumed security collapses once boundary conditions are tested, and how costly it is to rebuild certainty after that collapse. The war that followed did not escape those constraints. It operated entirely within them, governed by limits that could be managed, shifted, and postponed, but never removed. In the end, maritime victory did not belong to the side that acted most boldly, but to the one whose systems endured longer under sustained pressure, until the opposing structure could no longer absorb another cycle of strain.